So it's my pleasure to start today's seminar and to welcome here Dr. Ioannis Gialamas, right?
Yeah.
From the technical or from the Technical Institute in Tallinn. And today he's going to talk about Bimetric Gravity, right?
Yeah.
I would like to suggest the length of the seminar for, well, let's say 45 minutes, but it's longer, it doesn't matter. Also, I would like to ask people, the audience, to turn off the video. It's turned on, it's turned off, yes, great. Just if there are any questions after the talk, you can turn it on just because of the transmission. So thank you very much for, like, let's say, coming here. And I can ask you to start your talk. Thank you very much.
Okay. Okay. Hello. I would like to thank you and thank the organizers, of course, for this nice series of seminars and for giving me the opportunity to present my work. The title of my talk is Bimetric Gravity and its extension to metric-affine gravity. And it's based on this paper, which was written in collaboration with Kyriakos, and now it is published in Physical Review D. These are the contents of my talk. I will start with an introduction to the linear massless spin-to-field theory, which is equivalent to general relativity if we perturb the metric tensor around Minkowski space. Then I will show you the extension to the linear massive spin-to-field case, which initially proposed by Fields and Pauli. And we will see how the Gauss degree of freedom goes away. And after that, we will be ready for the main topic of this talk, which is bimetric gravity or bigravity, and its extension to bimetric-affine gravity with quadratic in curvature terms. I will try to give as much as possible details by showing you many computations.
Okay, sorry for interrupting you. I can see your screen. Probably it's just my mistake, I'm not sure, but at the moment it's disappeared from my screen.
Really?
So I'm not sure how the others.
Yeah, we cannot see it, Yanni.
You cannot?
No, we cannot.
What's the problem?
We can see you.
Okay.
And now, yeah, now it's better. Okay.
Now it's okay.
Okay.
Yeah.
So just to be sure, can you turn on your first page or skip to your first page? Yeah. Okay, so it was National Institute of Chemical Physics and Biophysics because it disappeared from my screen, okay. So I was not able to correctly probably pronounce it. Okay, so please, you can continue. Thank you.
Okay. These are the contents, okay. Now, in this table, you can see various massless and the corresponding massive theories of particle physics. For example, for scalar fields, that is spin zero fields, like the Higgs boson, the massless equation of motion is the known Klein-Gordon. And in the right column, you can see the massive extension of the Klein-Gordon one. Fermions with spin 1/2 are described by the Dirac equation, and the massive ones by the Dirac equation with mass. Okay. Spin 1 gauge bosons are described by the Maxwell equation, and the massive ones like the W and zeta bosons by the Procca equation of motion. Spin 3 halves spin 3/2 fermions are described by the Rarita-Zwinger equation, which is this one, and its massive extension, of course. These particles are not exist in the standard model of particle physics, but there are such particles in other theories like the gravitino in the supersymmetry, which is the super partner of the graviton. And finally, spin 2 fields with no mass are described by the Einstein equation arising from general relativity. And the question is, which is the corresponding massive theory for spin 2 particles? So let's start with the massless theory. Sorry. And then we will proceed to the massive one. The gauge transformation for a field with two indices is given by this equation. And for a coordinate transformation of this form, chi mu prime goes to chi mu plus xi mu, we obtain this equation, this transformation for the spin 2 field here in the box. The most general form of the kinetic term, free action, that we can write down is composed by contributions which are quadratic in h mu nu and with two derivatives. This is given by this action where h is the trace of the tensor h mu nu. And now the requirement of gauge invariance fixes the coefficients A1, A2, A3, and A4, except of course for an overall normalization factor that we choose to be such that A1 equals minus 1/2. Where the sign is fixed by the requirement that the energy is positive definite. Now, after rescaling of the tensor h mu nu goes to m Planck over square h mu nu, we recover the linearized Einstein-Hilbert action that we know for general relativity. The next step is to count the independent degrees of freedom which are actually propagating in this theory. So first we can use the gauge invariance I showed you before in order to choose the Lorentz gauge, which eliminate 4 of the 10 degrees of freedom, which are present in the tensor h mu nu. Of course, what I forgot to say is that in general, h mu nu has 16 degrees of freedom. But if we assume that is symmetric, then we have 10 degrees of freedom. And then the choice of Lorentz gauge gets rid of the 4 degrees of freedom. Therefore, there is a residual gauge invariance that is the functions xi mu satisfy this equation, box xi mu equals 0, which eliminates 4 extra degrees of freedom. So finally, we have 2 independent degrees of freedom. This can be easily shown by fixing the gauge completely. And in total, we arrive to the transverse traceless gauge given by this. As you can see, the first equation has 4 constraints. The second has 1 constraint, and the third one 3 more constraints. So finally, 10 minus 4 minus 1 minus 3 equals 2 degrees of freedom for the graviton, the massless spin 2 particle. Let's now move to the construction of a linearized field theory for massive spin 2 particles, the so-called Fritz-Pauli theory. The most general Lorentz invariant mass term that we can build is a linear combination of 2 scalar quantities, h mu nu square plus h square, where m is, of course, the mass of the spin 2 particle. Of course, the mass term breaks the gauge invariance we had before in the massless theory. And now, in order to find the numerical coefficients C1 and C2, we require the resulting mass term to be ghost-free. To do so, we start by introducing four Stackelberg fields, chi mu, associated with the symmetric tensor field h mu nu. In this way, the first term with a perpendicular symbol carries 6 degrees of freedom, while the second term with chi mu, which is also symmetric in the interchange mu nu, carries 6 degrees of freedom. Carries 4 degrees of freedom. 6 plus 4 equals 10 degrees of freedom. And that is the mass term that we get after including the 4 linearized Stackelberg field. Yeah, has this form here, from which we easily see that it is invariant under these simultaneous transformations of h mu nu and chi mu. Now, the mass term provides a kinetic term for the fields chi mu, which is given by this action. And if we split chi mu into a transverse mode, bearing 3 degrees of freedom, and to a longitudinal mode bearing 1 degree of freedom, we obtain this action for the longitudinal mode. From this, we see directly that unless C1 equals minus C2, the kinetic term for the field bears time and space derivatives of order higher than 1 because of box square. And as a consequence of Ostrogradsky's theorem, 2 degrees of freedom are actually hidden with an opposite sign kinetic term. And one of them is, of course, ghost, that we need to get rid of by tuning the relative value of the two parameters C1 and C2. We can also explicitly see the appearance of this ghost degree of freedom by introducing a Lagrange multiplier, bar chi equals 2 box chi. And after performing this change of variables to the scalar fields phi1 and phi2, this shows us that the two scalar fields always enter with kinetic terms with opposite sign, these terms here, which means that one of them is always a ghost degree of freedom. And in order to prevent this instability to arise, we need to make the specific choice C1 plus C2 here equals 0, which is the so-called Fritz-Pauli tuning. Now, the only possible mass term is given by this action with the Fritz-Pauli tuning applied. And in the unitary gauge, chi mu equals 0, we obtain the final form of the mass term, which is here. The full action after, again, the rescaling h mu nu goes to m Planck over 2h mu nu, and redefining the mass parameter, we obtain this action where the first term is the kinetic term and the second term is the mass term for the spin-2 field. This calligraphic epsilon is the so-called Lichnerovich operator. The crucial point is the form of the mass term here, which, as I said, it has to be h mu nu squared minus h squared in order to avoid the ghost instability. Every other combination will give us a ghost degree of freedom. Now, in this slide, you can see why the Fritz-Pauli theory is not so popular anymore, the theory we just saw. The first thing is that the massive spin-2 propagator diverges in the massless limit. That is, if we take the limit m, the mass goes to 0, we do not obtain the graviton propagator, the normal graviton propagator. This discrepancy is usually known as the Van Dam-Veltman-Zakharov discontinuity, or VDVZ discontinuity. And it is translated into a similar discrepancy for the Newtonian potential, which is larger by a factor of 4/3. This factor can be eliminated, of course, through a redefinition of the Newtonian gravitational constant G capital of the massive theory with respect to the one of the massless theory. But the discontinuity will then reappear in other observables, for example, the deflection of light by massive objects like stars, like the sun, which will be then 25% smaller in the massive case than in the massless one. An answer to this was given by Weinstein in 1972, where he pointed out that at a certain distance from the non-relativistic source called the Weinstein radius, the linear regime breaks down. And for any radius below the Weinstein radius, the theory enters a non-linear regime. So, since the Fritz-Pauli theory of massive gravity is by construction a linear theory, it is normal that its predictions do not pass the observational tests inside the solar system. Therefore, the solution is to include non-linear corrections in order to restore agreement with solar system observations. The Weinstein mechanism allows us to recover GR predictions around massive bodies like the sun and other. Starting from the nonlinear GR, we arrive at the linearized general relativity, which describes the usual graviton field. Then Fritz and Pauli give us the first massive gravity theory, which contains a spin-2 particle with 5 degrees of freedom instead of 2 of the normal graviton. Then in the nonlinear level, Dvali-Gavadadze and Porati, with the use of extra dimensions, studied their massive gravity, their theory, and 11 years later, Deram and Gavadadze and Tolley introduced their model, which contains a second rank 2 tensor. But I will not discuss about this. And finally, Hassan and Rosen studied the so-called bimetric theory of gravity, in which the second rank 2 tensor is dynamical. In our work, we extended the bimetric gravity to a metric-affine framework with the addition of quadratic in curvature terms. Let's start with the bimetric theory of gravity, or just by gravity. In this theory, the axiom contains 2 tensor fields, G and F, and 2 rich scalars. That are kinetic terms for each rank 2 tensor field, the rich scalars. Of course, 2 mass scales and the potential which contains the interactions between G and F, where this delta here is the matrix product of the inverse G times F. And the potential is the sum of 5 specific terms, as we will see in the next slide, Yeah, and also in the absence of matter couplings, of matter couplings, the structure of the bimetric action is invariant under these interchanges here in blue color. Okay, this is the potential, where beta n are parameters and this En are functions of delta given by this relation here, equation 3, and with E0 equals 1. The potential has this specific form in order to avoid the gauss degree of freedom we saw before, which is also called Bulwer-Dieser ghost. Here you can see the 5 functions En that involved in the potential. The first one is just 1. The second one is the trace of the square root of delta. The third contains traces squared. And the fourth one, as you can see, it is proven that it's just the determinant of the square root of the matrix delta. As you can see from the construction of the action, the term E0 is a cosmological constant for the metric g mu nu. And the term E4, which is square root of f over square root of g. So since the square root of g is also in the action, only the square root of f survives, and thus this term, E4, is a cosmological constant for the second metric, for the metric f mu nu. Two notes are this. The parameter m is redundant. That is, I mean that it can be absorbed by the beta parameters if we redefine them. And also the functions E1, E2, and E3 are those which contribute to the mass term, as we will see in what follows. While E0 and E4 give contribution mainly to the cosmological constants. Now we will proceed to the linearization of the theory by considering small fluctuations of the metric around a common background, g mu nu bar. That is g is approximated by g bar plus h, and f is approximated by g bar plus L. Also, we will use the inverse metric, which is also included in the tensor delta we saw before, and is given by this equation here, up to second orders in the expansion. Okay, and also we will use these relations for the determinants of, for the square roots of the determinants of the two tensors. What we really want to do is to expand the kinetic terms, that is the rich scalars for both metrics. So first we expand the Levi-Civita connection, which at first order contains derivatives of h, and at second order is h times derivative of h. So doing all of these things, we obtain the perturbed Einstein-Hilbert term, which is given at second order by this equation here. And this can be simplified a lot after, of course, a partial integration. So this is the final form for the scalar. And following similar steps, exactly the same steps, we get the Einstein-Hilbert term for the second metric f. Both of them can be written in terms of the Lichner-Rovitch operator, we saw before. But this time, the Lichner-Ovitz operator contains the background metric G bar and not the Minkowski one as we saw previously. So we just saw that the linearization of the Einstein-Hilbert term drive us to the same result we obtained before, assuming only the gauge invariance of the metric tensor. Now, the last step is to linearize the potential, which contains the interactions. So let's see an example of a term that is included in the potential. For the computation of the trace of the square root of GF, first we expand both G and F, and then we do the product and we arrive at the second line here, which is, if you see carefully, it is the square root of 1, the unity matrix, plus something small. So we can make a Taylor series to obtain finally the last, and after doing the traces, we obtain the last line, which is an expansion up to second order. And of course, in a similar way, we can compute all the other terms that are included, are contained in the potential. To sum up, all the terms included in the potential are given by these equations here, where we have expanded up to second order. So after linearizing everything, what means everything? The Einstein-Hilbert terms, two Einstein-Hilbert terms, and the interacting potential, we obtain the action given by equation 13, which is the linearized form of the bimetric action. The first line are the kinetic terms for the two tensor fields, and the second line are terms related to the cosmological constants, and the third line is the mass term. Now the parameter coefficients B, AG, and AF are given by these equations. That is, are functions of the potential parameters beta and the masses, and the coefficient C is automatically -1, which is, if you remember, the condition we need for the absence of the Gauss degree of freedom. We need this sign here to be -1. And it is by construction -1. Of course, if we want an action that describes the graviton plus a massive spin to particle, we set the coefficients AG and AF to 0. C is automatically -1, and B must be negative in order to have the correct sign for the mass term. Then we can rewrite the action in a more clear form by using the mass eigenstains M capital, M mu capital, and G mu capital. And we obtain the action in the box, which of course G is the normal graviton, the massless spin to particle, and M is the massive spin to particle with a mass M Fritz-Pauli given by this equation here. And as I promised, the mass term contains only the parameters beta 1, beta 2, and beta 3, not beta 0 and beta 4, which are contribute only to the cosmological constants. Let's see an example, the so-called minimal choice. We can choose the parameters beta 2 and beta 3 to be equal to 0. beta 0 equal 3, and so on. And then for these values, the cosmological constants are 0, and the Fritz-Pauli is given by this simple expression here. In this slide, you can see possible couplings to matter fields. The most straightforward coupling is to just couple either G or F to the matter through these terms here. And but this type of couplings breaks the interchange symmetry between the two tensor fields, but it is okay because it is still ghost-free. Now, if one wants to couple both G and F to matter, there are basically two options. The first is to couple G and F to different matter sectors, and this choice is ghost-free. And the second option is to couple both G and F to the same matter content. This type of couplings is somehow problematic as it is not anymore ghost-free. Another choice is to introduce an effective metric formed out of G and F in this way here. And the advantage with the effective metric is that matter couples symmetrically to G and F. This coupling does have a ghost also, but the coupling could potentially still be used effectively below the energy threshold of the ghost. And finally, assuming that coupling to matter, this type of coupling of matter, we can read off the physical Planck mass, which is just the square root of mg square plus mf square, the two mass scales of our initial action. Okay, now let's see all of these things in a different formulation of gravity, what we did in our work. The metric-affine gravity, in which the connection gamma is an independent variable and can be decomposed into the Levi-Civita connection plus a tensor which is called distortion tensor. And then the Ricci scalar can be written in this form, where Rg is the usual Ricci scalar in metric-affine, in metric formalism. And the rest terms contain the distortion tensor. Some general stuff in metric-affine gravity are listed here, is that there is also torsion if the connection is not symmetric, non-metricity if the covariant derivative of the metric tensor is not 0. Also, in general, one can add 20 additional, I think it's 21, but okay, additional dimension 2 scalars in the action, but this is beyond the scope of the seminar. And some other things. Now, if we set the non-metricity to 0, we obtain the so-called Einstein-Cartan theory. The whale gravity is obtained for zero torsion, while if both non-metricity and torsion are 0, we obtain the Riemannian gravity, which in any case is equivalent to the metric-affine one if the action contains only the Einstein-Hilbert term. In our work, we extended the usual by gravity to its bimetric-affine counterpart, where now both the Ricci scalars can be decomposed to the usual metric Ricci scalars, Rg and Rf, plus distortion-dependent terms. C is the distortion that is connected with the one Ricci scalar. and the C tilde is the distortion connected with the average scalar. Varying the action with respect to the distortion, we obtain, and substituting it back to the action, we obtain the usual by gravity as expected, because, as I said before, when we have only the rich scalar in the action, then metric-affine and metric are equivalent. Now, if we add the quadratic term to the action, the situation is different, as now the two formulations are not anymore equivalent. So this is the quadratic term, and M tilde is its coupling. The action can be written in this equivalent form, in which we have included an auxiliary field chi. The next step is, of course, to integrate out the distortion C and C bar, the two distortions. Solving for C tilde gives the same result with the Einstein-Hilbert action, since there is no R² term for this rich scalar of the F metric. While solving for the distortion C, we obtain this equation, which has this solution, equation 17. And if we substitute it back to the action, we obtain the action, this action here, 18. The next step is to do a value scaling as usual of the metric G mu of this form in order to go to the Einstein frame given by equation 19. The functions En after the value scaling are transformed in this way, where now omega is this factor here, 1 plus psi over m tilde square. And so the potential term gets a factor 1 plus psi m tilde square to the power n over 2 minus 2. This is in the Einstein frame. And now, varying the action with respect to the auxiliary field chi, we obtain the equation 20. And if we solve it, of course, and substitute it back to the action, we obtain the full nonlinear bimetric-affine theory of gravity. But the easy thing is to linearize the action with respect to the auxiliary field, keeping up to quadratic orders as we did before. The action then is of this form, where these kappa n are given by this expression. And now we can easily vary the action with respect to chi, which will give us this solution here, which we will use in what follows. If you see, we expect that chi does not depend on beta 4, since if we substitute n equals 4 in equation 23, we get 0. 4 over 2 minus 2 is 0. So varying also the action with respect to the tensors G mu nu and F mu nu will give us the Einstein equations for the two tensors, in which these tensors V and V tilde are functions of G and F. For example, V mu nu 0 is just the metric tensor G mu nu, and V mu nu tilde 1 is F, is f times x, where x is the square root of the matrix delta we have defined it in the beginning. The next step is to linearize the two tensors G and F. And we will use that the backgrounds G bar and F bar are the same. And if we do that, we obtain these simplified Einstein equations with lambda G and lambda F being the cosmological constants. And consistency between these equations, the two Einstein equations, requires lambda G to be equal to lambda F, which fixes one of the beta n parameters of our model. Of course, the five functions En are now just zero-order numbers, 1, 4, 6, 4, and 1 in turn. This is the equation for the auxiliary, which if we substitute the values 1, 4, 6, 4, 1 for En, gets this very simple expression. Which is a function of the beta n parameters, except of course beta 4, and the redundant parameter m and m tilde are also here. Don't forget that the parameter m tilde is the one that is related with the r squared term, the quadratic term. After quite a bit of algebra, we arrive at the linearized action, which has the same general form as the Einstein-Hilbert bimetric case we saw previously. And the appearing parameter coefficients alpha g tilde, a g tilde, af tilde, c tilde, and b tilde are given by very complicated expressions of all the involved parameters, where now we have also defined a new parameter lambda, which is m square over m tilde square. As before, the second line in the action 25 are terms that are related to the cosmological constant. And again, as before, the spectrum can consist of a massless spin-2 and a massive spin-2 particle without the presence of any ghosts. If the parameter c tilde is -1, and of course b tilde must be smaller than 0, must be negative. In contrast to the standard bimetric gravity, in which we saw that c, the corresponding function parameter c, is automatically -1. In this case, c tilde is given by a very long expression. Here is the parameter function c tilde. It is quite long. As you can see, it is too complicated. But the solution for it, for the constrained equation c tilde equals -1, is unexpectedly very simple. As you can see from equation 26, if we fix the parameter lambda, remember that lambda is m square over m tilde square. If we fix to have this value, then the theory in the linear level is free of ghost degrees of freedom. Also, we have to substitute the solution for lambda to the equations of ag tilde, af tilde, and b tilde. And if we do that, we obtain these expressions, which are not so long. And now the Fields-Pauli mass is given by this relation here in the box, while in normal by gravity was much simpler, given by this equation. But in both cases, it is a function of the parameters beta 1, beta 2, and beta 3, as we saw previously, and of course the mass scales of the action. Now let's see again the same example. Remember the minimal model for the parameters, that is beta 0, 3, beta 1 equals -1, beta 2 equals beta 3 equals 0, and beta 4 equals 1, which was a valid scenario in the normal by gravity. While now it gives us 0 cosmological constants again, because Ag tilde equals Af tilde equals 0. But the crucial parameter C tilde is -1 only if lambda is 0, which means absence of the R² term, which in turn means normal by gravity. So the conclusion is that the minimal model with this choice of the parameters is not valid in bimetric quadratic gravity. So let's go beyond the minimal model. As a case 1, we take beta 2 equals beta 3 equals 0. And in this case, the constraint for the C tilde fixes beta 0 to the value 1 over 2 lambda. The Fritz-Pauli mass is given by this equation, from which we understand that beta 1 must be negative. Also, the parameter beta 4 is not so important because it can be fixed by the requirement of equal cosmological constants for the two metrics. And if we want a vanishing cosmological constant, don't forget lambda g equals lambda f equals lambda. So if we want a vanishing lambda, we have to fix the parameter beta 1 to be -1 over 7 lambda. And in this case, the Fritz-Pauli mass has this very simple form where alpha is just the ratio of the two Planck masses, mf over mg. Now, if we go beyond the case beta 2 equals beta 3 equals 0, we obtain this equation for beta 0, and as before, the beta 4 is fixed by the cosmological constant equality. And if we use these rescaled parameters, lambda bar and beta bar, we obtain, which are rescaled with the help of the parameter beta 1, we obtain this relation for the cosmological constant, and this one for the Fritz-Pauli mass squared, which is positive definite, not only if beta 1 is negative, but we are free to choose one of the two cases you can see here. Of course, if beta 2 equals beta 3 equals 0, only the second choice is valid. Now, for a vanishing cosmological constant, we obtain this equation here, which which can be plotted for various values of parameter lambda tilde. And as you can see, the value of lambda tilde does not play much role. And also from this plot, we can see that the parameters beta 2 and beta 3 have always opposite signs. Now, solving the equation lambda equals 0, we obtain this equation for the parameter beta 3 bar, and also we have some values for the parameter beta 2 bar that are excluded because we want a non-zero Fritz-Pauli mass, and also no divergences in the mass and the cosmological constants. For these values here, the denominators for the Fritz-Pauli and the cosmological constant are 0. So this is a problem, and we have to exclude these values. And this is the equation again for the Fritz-Pauli mass we saw before. And in these plots, we illustrate the mass in the units of beta 1 and the masses of the model. Is this also the Planck mass here? The left panel coincides with the choice 1 of the parameters, which means beta 1 positive, while the right one is for beta 1 negative. If beta 1 is positive, then beta 2 is negative, and beta 3 is also positive. And the opposite happens in the case of negative beta 1. And now, before we conclude, a little bit of phenomenology. If we take lambda bar to be around 10, and beta 2 over beta 1 of order 1, we obtain the Fritz-Pauli mass squared to be m Planck squared times 10 to the minus 3 beta 1. Thus, it seems that relatively light Fritz-Pauli that can play the role of dark matter could be obtained only for very small model values. For example, we obtain m Fritz-Pauli about 10 TeV for beta 1 10 to the minus 25. And as a consequence, m tilde is about 10 to 5 GeV. And here's a summary. We saw the importance of a non-linear massive theory of gravity, like bimetric gravity. We saw that the bimetric-affine theory of gravity is equivalent to the standard bimetric gravity. But if we add quadratic in curvature terms, then the bimetric-affine gravity is ghost-free only if we choose the coupling of the quadratic term lambda to have this specific form. And finally, as in the usual by gravity, the massive spin-2 particle can play the role of the dark matter particle for suitable tuning of the parameters, the beta parameters. That's all. Thank you very much.